Last time we were graphing these functions by making transformations of parent graphs. And what we're doing today is essentially the same thing. It's just a slightly streamlined process, okay? So the way we're going to look at this from now forward is we're going to define these functions that we're interested in graphing. In this case, we're going to talk about absolute value functions first. We're going to define what's called a vertex form of that function that already includes the parameters A, H, and K that we've been talking about, right? Remember, A is the vertical dilation factor, H is the horizontal translation, and K is the vertical translation, right? So instead of just starting with a parent graph and tweaking it with those values, we're going to start with a vertex form of the graph that already includes them, okay? So this is our vertex form for an absolute value function, and this should make sense to you, right? Because A is the number that we always multiply by the function out front, and look what it's doing. We're multiplying it by the absolute value function. H is the value that we are subtracting from X inside the function, so inside the absolute values in this, absolute value bars in this case. And K is the number that we're adding outside of the function, so in this case, outside of the absolute value bars, right? And then we should be able to just plug those values in for A, H, and K to immediately come up with f of x, all right? So if we go back to what we were doing last time, we always found that when we did our translations, and I pointed this out to you guys a couple days ago when we were doing this stuff, when we did our translations, if we translated to the right by H, oh, you can't see my screen? Oh my gosh. Thank you. The second time I've done that today. So let me start over. None of that stuff was going to make any sense if you couldn't see what I was talking about. Must be Friday, huh? So here's our vertex form, right? Instead of doing what we did last time, we're starting with an absolute value graph and doing all these transformations. We're just going to start, like I was saying, with an absolute value function written in what we call vertex form, where the A and the H and the K are already included, right? A is what's multiplied out front. H is what's subtracted from X inside the function, so inside the absolute value bars. And K is what's added to the function outside, so outside of the absolute value bars, okay? Now, think what happened a couple days ago when we were graphing these things. H is the horizontal translation, right? And so if we translate this thing horizontally by H, let's track what's going to happen to the vertex of an absolute value function, right? The vertex of an absolute value function always starts off at the origin, right? So if I slide this thing horizontally by H, let's say H is 5, well, then the vertex ends up with an X coordinate of 5, doesn't it? Right? K was the vertical translation, so that's how far we're translating the function vertically. Let's say that K was 3. Well, after I slide the vertex over to the right by 5, I would have slid it up by 3, right? Well, what are the coordinates of the vertex going to be? 5, 3, aren't they? Right? So H and K, because the vertex is starting off at the origin, which has coordinates 0, 0, H and K tell us not only how far we slide the function, but they give us the location of the vertex when we're done sliding, right? So the coordinates of the vertex are always just HK. How easy is that? So once we determine what the values of H and K are, we can just immediately in one step move the vertex to that location, right? Now, what about what happened with A? And let's do this example. Let's go ahead and do this example real quick, and we'll go back and figure out how we can relate A, what we can do to take a shortcut with A. How about? So let's take this example, f of x equals negative 7x plus 4. Well, here is our absolute value function written in vertex form. So what are the values of A, H, and K for this function f of x? Type it in chat for me. What's the value of A, please? Just the value of A. Tell me first. Yeah, good. It's just negative 7, isn't it? Good. Okay, when I want the values of h and k, instead of writing those separately like we used to do, now I'm going to write it as an ordered pair because those are the coordinates of the vertex, right? So what are the values of h and k for our function up here? Type them in chat for me. Yeah, good. 0 and 4, right? Good, because we're subtracting nothing from x, and 4 we're adding outside the function. Good. So when we write the values of h and k as an ordered pair, that just gives us the location of the vertex, doesn't it? Okay, so what can we do here then? We can graph this thing super easily, right? We'll take this function, we're going to drag the vertex to its home at 0, 4, which is right there. Everybody agree? Okay. And then now all I have to do is I've got to vertically dilate this thing by -7. Okay, so how do I do that? Well, normally I would go over by 1 and up by 1. I'd go over by 2 and up by 2, right? What's the job of the vertical dilation factor? It's going to multiply my normal parent height of my function to get my dilated heights. In this case, it's going to be a reflected and stretched height, right? So if I take this point right here that the ant walks to first by going right 1 and up by 1, if I want to find out where he ends up on my dilated function when he goes to the right by 1, I'm just going to multiply this height 1 times a, which is -7, right? To get the answer, 1 times -7 is -7. So when he goes to the right by 1, he's going to go up by -7, which means he's going to go down by 7, right? So he's going to go 1, 2, 3, 4, 5, 6, 7, right to there. And there's going to be my point. Everybody see that? Okay. And I've got this. I'm going to go back just a little bit here. I think, did I not? Oh, yeah. Let's go back to this page for just a second. So we've got an axis of symmetry on all of these V-shaped graphs also, don't we? What do we mean by that in math? An axis of symmetry. An axis just means a line, but an axis of symmetry is the line that's going to split this thing in half, right? Every absolute value function has a line of symmetry, a vertical line through its vertex. Everybody agree? Right? A line of symmetry through the vertex. So if I take, for example, let's say I take this absolute value function. I'm just going to make one up here real quick. Let's say I take one that's got a vertex at 2, 3. Then here's my axis of symmetry, right? What are the coordinates of that vertex again? The coordinates of the vertex are, in this case, are hk equals +2, +3, right? Okay. Well, the equation of that line, it's got to go through the vertex, so it's going through the x value of 2, isn't it? So the equation of that line is just going to be x equals 2. It's just a vertical line, so it's just x equals a number, right? And it's x equals 2. In fact, that's always going to be true. The axis of symmetry is always going to be the line x equals h. Okay? So if I go to this example right here, well, here's my vertex, right? I go over 1 and I went down 7. I could use that axis of symmetry line. There it is, right? There's my axis of symmetry. It's just the line, in this case, x equals 0. Not that I even need to know the equation in this case, but it's x equals 0. And what does that line do? That's the line that I could fold this thing over so it would fold onto itself, right? Everybody agree? That's what an axis of symmetry means. It splits it in half so I get identical copies on the left and the right, right? So every point, in other words, on my V-shaped absolute value graph is going to have a reflected point on the other side that would line up when I fold it. Okay. So then right here, this point should fold over or reflect over to a point right there. Okay, and that's all I need to graph this thing, right? It's just a V shape. And so this is what my graph looks like then. Right, that's it. Okay, no big deal. Now I want you to notice something here. The slope of my regular absolute value shape, the slope of the right side is just 1, isn't it? To get from the vertex to this point right here, I'm going to rise by 1 and run by 1. So that's the slope of 1, isn't it? To get to this point, I would rise by 2 and run by 2. Well, 2 over 2 is 1. To get to this point, I rise by 3 and run by 3. 3 over 3 is 1. So the slope of the right leg is 1. The slope of the left leg is -1, right? Well, when I multiplied by my vertical dilation factor of -7, look what I did to the slope. Look at my new slope now. On my final purple graph here, if I make a slope triangle, look what happens. I'm going to rise by, oh, what did I just do there? I don't know what that was. Yikes. There we go. So I'm going to rise by -7, and I'm going to run by 1. Look at the slope. Is that an accident? No. That's the value of A, right? The slope of the right leg is always equal to A for an absolute value graph. Okay, so we can go back to this last page here. And there's another little trick we have for graphing absolute value functions that makes them really easy. A is the slope of the right leg and its opposite. So -A is the slope of the left leg, right? And on this past example, the slope of the right leg is -7. The slope of the left leg is +7, right? It's the opposite of A. The opposite of -7 is +7, right? So that's always going to work for absolute value graphs. Okay, so tell me real quick here, just a quick little reinforcer. So let's take this function down here. Y equals the absolute value of x plus 1 minus 4. Everybody type in chat, what are the coordinates of the vertex of that function? Type it in chat for me. Oh, good. Yeah, that's it. -1, -4, right? Just the values of h and k. Good. What's the axis of symmetry? You got to write it as an equation because it's the equation of a line. So what's the equation of the axis of symmetry? Remember, the axis of symmetry is always just the line x equals h because it's got to go through the vertex. So what is it? Oh, good. X equals -1. And we have to write it with the x too, don't we? Right, because we want to write the whole equation. It's got to have an equal sign in it. So x equals -1. Okay, let's try another one. How about this guy? So what's a equal to? Type it in chat. Okay, good. -6, good. And how about h and k? And I'm going to write it as an ordered pair, so I'm writing the vertex. Okay, good. -1, -2. All right, good job. So then look what we can do. We know the coordinates of the vertex are -1, -2. I'll just drag this thing over to the location -1, -2. And while I'm at it here, I'm going to go ahead. Actually, that's okay. I don't need to worry about it. Okay, there's my new vertex, -1, -2. Now, A is equal to -6, right? So I know the vertex is going to be here. What's the slope of the right leg going to be? What's the slope of the right leg of this thing going to be? Type it in chat. So when the ant goes 1 to the right, how far is he going to move vertically on my dilated graph, the one that's been... Okay, that's how far he would move on the parent graph, right? But A is equal to -6 this time. So instead of going over 1 and up by 1, he's going to go over 1 and up by how much? Okay, that's closer. But A is -6, right? -6. There we go, right? Perfect. So again, instead of going 1 to the right and up by 1, we're going to multiply that normal height by A, which is -6. So that gives me -6 is my new height, right? And we can even just use our little trick of using the slope. I know that the slope of the right leg is going to be A, so that means I'm going to rise by -6 and run by 1, right? Because -6 over 1 is my slope. And I end up right there. Or if you want to think of it as a dilation factor, which is fine, I'm just going to go over 1 and I'm going to go up by -6. Either way, I end up right there, don't I? Okay. And I've got this axis of symmetry down the middle. So I can just reflect that point over the axis to get its partner point on the other side. And there you go, right? Now all I've got to do is just connect the dots and I'm done. Give me a 1 to 5. Okay, I'm not hearing from everybody. Okay, all right, pretty good. Okay, what about this guy? We're going to work backwards on this one. So this time, instead of them giving us an absolute value function in vertex form, and we write the graph, they're giving us the graph and we have to write the function. Okay, but the process is just almost the same. It's just in reverse. Values of A, H, and K that we can plug in to write the function, and that's it. We're going to find those by looking at the graph. So what about H and K? Remember, those are just the coordinates of the vertex, right? So what are the values of H and K here? Type it in chat for me. What are the values of H and K? Close. Oh, there we go. Good. -4, +3. Okay, good. Just the coordinates of the vertex, right? So there's H and K. What about the value of A? Okay, so how are we going to get that? Well, we could just look at the slope, right? If I pick 2 convenient points on the right leg, like right there and right there, look at the slope. We're just going to rise by 1 and run by 2. Everybody agree? So would everybody agree I just get 1 over 2? because remember, A is the slope of the right leg of the V. Okay? The other way we could do that, though, and the reason I show you the other way, you're probably thinking, why is he showing us the other way? That's the easiest way. You're right. It works for absolute value, but we're about to look at quadratic functions, which have different shapes. Those are U-shaped, and so they don't have slopes. So the slope trick isn't going to work. In those cases, we're going to have to think about this as a dilation, right? So let's just take this one and let's look at this one as a dilation also, just for a second. So I know that on my normal V-shaped graph, I go my parent graph shape. The slope is 1, so I go over 1 and up 1, over 2 and up 2, over 3 and up 3, right? So it has that shape and its reflection on the other side. Okay, well, look at this point right here that we used that was graphed, right? That's a convenient one because this point falls at the corner of the graph paper, right? It's got integer coordinates. So normally we would have gone 2 to the right and we would have gone up 2, right? Okay, well, to get the blue height, the dilated height, we would multiply 2 times A to get the dilated height of what? Well, the dilated height, when I go 2 to the right, the actual height of the blue graph that we're trying to write the equation of, right, the function, is 1. So 2 times the dilation factor, A, has to give us our compressed height of 1. What do I do to solve for A? I just divide each side by 2, don't I? And I can solve for A, and I get A equals 1/2. Either way, I get A equals 1/2, don't I? Right? So to write the function, then all I have to do is plug those numbers in. So I'm plugging 1/2 in for A. I'm plugging in -4 for H, and I'm plugging in 3 for K. And then what's that give me? If I do all that stuff, I get f of x equals 1/2 times the absolute value of x minus -4 plus 3. And subtracting a negative is like adding, isn't it? So my final answer just looks like 1/2 times the absolute value of x plus 4 plus 3. Okay, everybody good with that? Okay, and it takes a little practice. You'll get one like that on the assignment where you got to work backwards. So you get a little practice with it. Okay, all right, so last thing I want to just kind of introduce you to for today. And that is the idea that we can do the very same thing we just did with absolute value functions. We can define a vertex form. We can do that with the slightly more complicated quadratic functions, right? Same stuff though. A is still going to be the number that's being multiplied out in front of the x squared function. H is the number that's being subtracted from x inside the x squared function. And k is the number that's being added outside of the x squared function, right? And they mean the very same things. We know that h and k give us the coordinates of the vertex of the parabola. So now it's going to be the point of the u instead of the point of the v. And we still know, just like before, x equals h is the axis of symmetry, right? So this vertex form is useful because it shows us exactly where the vertex is. So it makes it easy to graph. And then all we have to do from there is from the vertex, we're just going to dilate our parent graph, x squared, to get the correct shape. Okay? So we know, of course, that when A is positive, the vertical dilation factor is positive. Well, we're not reflecting the parabola. It opens up. If A is negative, if it's less than 0, we're reflecting it, and so the parabola is going to open down. The U shape is upside down then, right? So answer this for me. This function at the bottom in the red box, first of all, tell me what the vertex is. How about? What's the vertex of this function? Type it in chat. So the function in the red box. Type the vertex in chat, please. Yeah, you got it, right? Just like before, just -7, -5, isn't it? Oops, wrong one. I guess I gave that away, didn't I? So it's -7, -5. And what's the axis of symmetry? Well, it's just x equals h. So it's x equals -7, right? Okay, what about this one? I'm asking what's the minimum value of the function? Now, what do we mean by minimum value? So if I have a function, if I have the graph of a function, the minimum value would be the lowest possible value of y, right, of f of x, which is the same as y. A maximum would be a highest possible value of y. So can anybody tell me here, what is the minimum value of f of x? What's the smallest y value on this function? Can anybody tell me? We'll talk about it in a second, but can anybody figure that out? What's the minimum value of f of x? So the minimum value of y for this guy. Okay, Tony got it. How come, Tony?
If x is 0, doesn't that kind of just make everything else 0? And then the -5 is just on its own.
Okay, that's an interesting way to do it. Sure. Yeah, you could say, well, if x is 0, well, no, if x is 0, it doesn't make everything 0. I'd just get 0 plus 7 squared. So that line of reasoning isn't going to totally apply, but there is something else we could do. A is equal to 3, right? You still got the right answer here. I think deep down you had a sense of why this is the case. If A is equal to 3, tell me, everybody type in chat, is this parabola opening up or down? If A is equal to 3, is this parabola opening up or down? Yeah, it's up, isn't it? When A is positive, the parabola opens up. Now think about the shape of an upward opening parabola for a second. If it's an upward opening parabola, then the vertex down here, right? Then the vertex down here, this point that's the vertex, is going to be the minimum, isn't it? Everybody agree? That's going to be the lowest point. If the parabola opened down, the vertex would be the highest possible point, and it would be a maximum, right? So in this case, the vertex is a minimum. Well, we know the coordinates of the vertex. The coordinates of the vertex are -7, -5, right? Well, that's got to be the lowest y value then, if that's the y value at the vertex, right? For this vertex down here, if the coordinates were -7, -5, then -5 is the minimum. Okay? So there it is. All right. Let's practice graphing these things. Let's try one. So let's try. Okay, we'll do this one first. Let's see. I want to do. There it is. Okay. Okay, here we go. So what are the values of A, H, and K for this guy? What's A? Type it in chat. Okay, not 0, right? A is the number that's being multiplied out front. So if I multiplied by 0, everything would just disappear, right? Oh, okay, it's 1. Good. There's an invisible 1 there, isn't there? Right? So A is equal to 1. How about H and K? Type those in chat for me. Let me get answers from everybody, please. Okay, good. Yeah, -2, 0. So good. We know that we're going to get a -2 here because that's a plus. That's going to be a -2. And then nothing is being added outside the function. So it's -2, 0. Okay, good. So then that means we can take this function and we can locate the vertex down here at -2, 0. Okay. A is equal to 1. So I'm done, right? I don't have to stretch or compress this thing at all. I'm multiplying the normal parent heights by 1, which means they don't change. So I'm done. That's it. Okay. So there's our graph. Just take a quick little picture of our graph. Okay, and the axis of symmetry would just be the vertical line right through the origin. Let me put that one in there too. There we go. Okay. Now let's answer all these questions. So we graphed this thing. You already told me the vertex. You already told me for part A up here that the vertex was -2, 0. Okay, what about the equation for the axis of symmetry? X equals what? Type it in chat. There you go. X equals -2. Okay, that's the equation of our vertical line, isn't it? Okay. What about the domain? That's what they're asking for part C. Okay, he's got to think back to last week, right? Keep in mind that this parabola goes forever, right? So what's the domain? The set of all the x values graphed on this function. If I projected that whole red parabola onto the x-axis, how much of the x-axis would be shaded? Type it in chat. What's the domain? Yeah, good. Okay, if we write it with interval notation, it's just -infinity to infinity. Or if I want to write it, I could also say all reals, depending on how they want the answer, right? One of the two things. Okay, how about the range? The set of y values on that graph. What about the set of y values on that graph? What's that going to be? Okay. Okay, I'm seeing some almost correct answers. There's one tiny thing that's wrong with those answers, though. Somebody want to fix it? Ah, there we go. Yeah, good. We have to include a bracket, don't we? Right? If we're using interval notation, so we had the correct numbers, right? The bottom limit of our range, the lower limit is -2, and the y values go up to infinity. So that part all looked good. But -2 is a point that the ant, that's a y value the ant could have, right? He could stand on the vertex, and so we have to have a bracket there to include that. If we want to write that as an inequality, I could just say y is greater than or equal to -2, right? Okay, the last two things then that they want on this. They want to know what is the largest interval of the domain where the function is increasing. Okay, so let's use interval notation here. What's the largest interval? And that, well, all they mean there is what are all the x values where the ant is increasing? What does it mean to be increasing, right? The ant's walking uphill from left to right. So for what x values is the ant walking uphill from left to right? Okay, are those answers at the bottom, are those for E, or are those for the range or for the increasing interval? McKenna, what were you answering? Were you answering part D or part E? For the range, okay. So now I need some answers for part E. Where is this function increasing? Give me the interval of x values where the function is increasing. Okay, when I'm asking for where the function's increasing, I'm asking for the x values now, right? All these things we're asking about up here, domain, range, the only one that's asking about y values is the range, right? But I want to know here for this one, I want the largest interval of the domain where the function is increasing. So on this graph, would you guys agree that this is the place where it's increasing, isn't it? That's where the ant's walking uphill. At what x value does that start? 0. Good, right? Starting at 0, and then it goes to the right forever. So the interval is 0 to infinity. Now the question is, do we include the 0? It's a good question, right? Should we include the 0 or not? Melinda, you got it right. So what was your thinking on that? How come you did not include the 0? You're correct.
Because is it because the ant isn't technically starting on 0? So that's why you wouldn't include it in a sense?
That's correct, right? At 0, the ant is not walking uphill. That's the bottom of the valley, right? 0 is the transition from decreasing to increasing. To the left of 0, the ant is walking downhill from left to right. Agreed? To the right of 0, he's walking uphill, and that's only the point of transition, so we do not include it. Okay, so then the last one here, how about on this last one, what color are we going to use? We'll just use purple. How about? So f of x decreases then on what interval? Well, he's decreasing over here, isn't he? All the way clear from negative infinity, he walks downhill until he gets to 0, right? But at 0, he transitions, okay? So how am I going to write that using interval notation? What goes on the left? You guys tell me. You guys write it in chat for me. How would I write that interval where the function is decreasing? Okay, let's get answers from everybody on this. Okay, good. But I got to include the parentheses, right? Because with interval notation, that's important. That's telling me whether I'm including endpoints or not. Yeah, good. So we get negative infinity is my lower endpoint because he's decreasing all the way from negative infinity up to 0 with parentheses, because at 0, he's neither increasing nor decreasing. Okay, good job. All right, let's try to maybe just get one more of these in for today, and that's probably pretty good. Okay. So what about this guy here? Let's go ahead and, first of all, let's write down the values of A, H, and K. That's where we always start, right? Because that tells us how to make the graph. So what's the value of A, everybody? Type it in chat. Okay, looks good. Negative 1/2. So what's that mean? It's going to be reflected because it's negative. It's going to open down, and it's going to be compressed, isn't it? So it's going to be compressed by a factor of 1/2. So all the points are only going to be half as far vertically from the vertex as they are in the parent graph. Okay, so what are the values of H and K? Type that in chat. Okay, good. -1, -2. So that represents the coordinates of the vertex, right? -1, -2. All right, so we can drag the vertex to that location. -1, -2. There it is. Okay. All right, now what? Okay, so now I've got to dilate this thing, right? A is equal to -1/2. So fill in the blanks for me here. When the ant goes 1 to the right, I'm going to write down the value of A again. You can see this. I want you just to focus on this graph, though. When the ant goes 1 to the right, instead of going up by 1, how much is he going to go up after I dilate the graph? Fill that in for me. He's going to go 1 to the right and up how far? Okay, let's find out. He goes 1 to the right normally on the parent graph. I'm always starting with the shape of the parent graph, and I'm going to tweak that with A, right? So when he goes 1 to the right, he goes up by 1. I've got to multiply that by my dilation factor, though, right? So I'm going to multiply 1 times -1/2, which gives me an answer of, supposed to be an equals, -1/2. So he goes up by -1/2. 1 right and down 1/2 to right there. Okay. All right, now let's do the same thing again for my next point. Normally I would go over to the right by 2 on my parent graph, right? My parent graph of x squared. I would go over to the right by 2 and up by 4, right? Up by 2 squared. How far am I going to go up on my new graph if I'm dilating it by -1/2? Type that in chat. So the answer, so McKenna had that first one correct. It was -1/2. If I go 2 to the right from the vertex, how far am I going to end up going up this time? If my dilation factor is -1/2. Let me get some answers here. Well, I'm getting no answers. Remember, the dilation factor, the only job of the dilation factor is it's going to multiply. We multiply it by the regular heights of the function to find the dilated heights. Yeah, so -2, isn't it? Right? How come? Because normally the ant would go 2 right and up 4, but this is going to change things. A is going to change things, right? Now he's going to go up 4 times A, which is -1/2, right? Times 4 gives us 4 times -1/2 is -2. Yeah, so he's going over 2 and up by -2. And so there's my point, right? Everybody get that? He would go over 3. That's not a very convenient one. Over 3 and up by 9 times -1/2 would be -9/2. That's not a very, -4.5, right? Not super convenient. Over 3 down 4.5 would be right there. Okay. And then all I have to do, I know it's time to go, but let me just finish this up here. So there's my, oh, darn it. So there's my vertex. I can just reflect these points. Let's just take this guy and let's reflect it over. Oh, what happened? That got moved, didn't it? There we go. There, okay. So this point just gets reflected over to there. And now all I have to do is just connect those points with a parabola, right? So there's my, oh, that's pretty good. I'm pretty impressed with myself. There's my parabola. Everybody see that? Okay, we'll call her quits. Have a great weekend. I'm here after school if you need any help. If I don't see you after school, I will see you on Tuesday.